What?
All right, so here's the deal. We've got a small car pushing a large car while speeding up to the right, and obviously there's a hand pushing on the small car. In a situation like this, there's one of these is better to draw first, and it's the one that's not receiving the extra force. Looking at this right now, which one's receiving an extra force? The small car, because it has the hand pushing on it. So we're going to start with the one without the extra force, which is the large car. So make sure you identify your system as the large car. And we know the large car has mass, which means what has to be pulling on it? Gravity. And gravity always pulls straight down. So we have force of gravity on the large car by the earth. And if we've got gravity pulling down, is the large car going to accelerate up or down?
No.
So the net force along the y-axis would be what?
0.
And what about along the x-axis?
0. Wait, what? Oh, no, not 0.
So the net force along the x-axis is going to not be 0. Cool? Because up and down it's not accelerating, but it is from side to side. So if it's not accelerating vertically, what's going to be bigger? Gravity, normal, or are they the same?
Same.
Same. So we got force normal on the large car by the, I'm going to call it the track. Some people called it the road. I'm good with either one. I'm going to put 4 hash marks on here because I'm not really sure how many we're going to need later. And it's better to, some of them later might be smaller. What else is pushing on the large car?
There's the
hand.
Is the hand touching the large car?
Oh, the small car.
friction.
Small car. Which way is the small car pushing the large car? To the
Right.
to the right. So let's go ahead and draw that in there. We've got force normal on the large car by the small car. And that happens to be the force that we talked about from this force versus time graph up here, right? Or in our results, force normal on the large by the small. What if that large car is moving, that block of wood's moving to the right, there has to be friction going which way?
To the left.
To the left.
Just a little though.
Now, so we've got a force of friction on the large car by the track, or maybe you called it the road or whatever. How big does it have to be compared to this normal force to the right?
Oh, less than.
It has to be less. Now, Rashawn said half, and I like that idea so that it's obvious to people that it's half. So I'm going to measure the normal force and use my fingers to measure it out over there and make sure that the force of friction is smaller on the large car by the track than the force normal on the large car by the small car. And once again, this force normal on the large car by the small car, that is the force from our force versus time graph. Do we need to do anything else with our large car? Are we good?
Yeah.
Number next.
Wait,
Let's, yes.
You know, like it's like force of gravity, large Earth, but what's the friction one? What's the T?
From the track. So, and you need to make sure in this case that whatever you said the normal force was, see how our normal force was, I used track up here because that's what we had on the tables, right? Blocks of wood on a track. All right, if you called it a road for your normal force, then your friction also has to be road. So whatever you said that was causing the normal force, that same object has to be causing the friction force. Speak.
Why is there a normal force going to the right?
Well, what's pushing on the large car? The small car, and what's between those rubber stoppers? That's a surface, and we know that the normal force is always what direction? Perpendicular to the surface. So we're talking about right here where we've got that connection, that that normal force is pushing that way. I'm going to get rid of that off the screen so it doesn't get saved. But, all right, number next, let's move on to the small car. Now, we know that the small car is smaller. Do you think that the small car had more or less mass than the large car? So how's that going to be compared to this? So gravity of the small car has to be smaller than that on the large car. So the weight of the small car, I'm going to go ahead and put 3 hash marks on there. Is the small car accelerating up and down? Is it accelerating along the y-axis? Nope. So the normal force has to be how big? Same size. Force normal on the small car by the track. And 1, 2, 3 hash marks. And since this whole lab was talking about the interactions between objects, we have this force versus time graph up here. We said, Normal force on the force normal on the small by the large equals force normal on the large by the small. Where is that going to show up over here? Which direction is there a normal force acting on the small car by the large car? Which direction? Point. Everybody. Which way is it pushing? Right, this way, right? So we have to measure this force, and it has to be exactly the same size over here. Now, I may have something inherently wrong in this problem. Be aware, this normal force, never mind. But, yeah. Anyway, this normal force should be bigger than what we're drawing over here, but we're going to sketch this out anyway. Force normal on the small car by the large car. All right, and once again, it has to be exactly the same size as the force normal on the large by the small. Those are, once again, the forces that showed up from the force probes and showed up on our screen for our force versus time graph. Those are the two forces showing the interactions between these objects. What else is pushing on the small car to the right? Excuse me, to the left?
There's a applied force of the hand.
Yeah, that's pushing to the right. What else is pushing the small car to the left? Friction. So, there's a force of friction. Now, would friction on a small car be bigger, smaller, or the same as the large car? It would probably be smaller, right? Because if it's got less mass, there's going to be a little less friction there. So, as long as we make it smaller than what it was on the other one, we have force of friction on the small car by the track. Why do we have to use a lowercase f for friction?
Because otherwise
Because we use capital F for force most of the time. Excellent. Now, next up, what's the one other force? Ellie, you already told us. What's the other force acting on this?
force applied from the hand.
Great. We have a force applied or a force of push on the small car by the hand. Now, I want to take a moment. When you're caught up, put your pencil down because I want you to think about this before we write it down. How big does the force of push on the small car by the hand to the right have to be compared to the other forces we've drawn up here so far? How big does that force of push on the small car by the hand have to be? Just think about it for a second. Think about what we know. We know that these two cars are accelerating to the right. We said that there was the net force along the y-axis was 0. The net force along the x-axis could not be 0 because it's accelerating. How big does the force of push on the small car by the hand have to be?
Well,
How many people have an idea in their head what the answer is? Hands down. Who would like to share something that we should consider? Grace, tell me one thing.
well, it's accelerating to the right.
Yes, ma'am, it is accelerating to the right.
So-
That's an important thing to consider. Excellent. Ellie, you were going to say? Okay. Somebody else. What do we need to consider? How big should this force of push on the small car by the hand be? Grace?
Bigger
Than?
than normal force with force of friction.
Okay, so first she said it's bigger than the force normal on the small car by the large car. So that was this long. That's the normal car. And you said plus the force of friction. So you want me to also add the force of friction on the small car by the track.
Yeah.
That would be that long. Should I draw the force of push on the small car by the hand to make it that long so it's equal to the sum of the forces to the left?
No, it has to be bigger.
And it has to be longer because
The net force is the sum of them, and it has to have it's accelerating.
there has to be a net force to the right because it's accelerating to the right. So our force of push on the small car by the hand has to be bigger than the sum of the two forces to the left. You guys did a great job. Way to go.